Alright, let me do this question. So this is chapter 5, problem 94. Again, I'm kind of going back in semester and finishing up all the questions that I wasn't able to do back then. That's basically my project this semester, to go back to the chapters 5 and earlier and solve all the new questions that I've added. So this one says an 8-some mass object. Let me just doodle just to make sure I have correct understanding of the physical picture. I have some object of some mass which has some initial velocity eastward, and let me just do my axis so that east is my normal plus x direction and north is my normal plus y direction. So east at 10 meters, some speed, then a force act on it for 2 seconds, after which it's telling me, and then it's gonna be moving northwest, so the force must be being applied like in that direction. Alright, after which it moves northwest 45 degrees in the so I guess it's probably useful to kind of diagram. So I have my initial velocity here and the final velocity also at 10 meter per second, so it's gonna be in this direction, 45 degrees in the same magnitude. What are the magnitude and the direction of the average force that acted on the object over the 2-second interval? So they've basically given us enough information for us to calculate this pretty easily. The average acceleration given by change of velocity divided by change of time. Now they're asking us for force, and to get force all you have to do is take this, multiply by mass. That'll give us the average force that they are actually asking us for. So let's just go through step by step. I think the very first thing I should do is figure out this delta V. This is my delta V, and I can get that from the V final as a vector minus V initial as a vector. And since this kind of looks like a vector question more than anything, let me just do this formally using all the formal notations, using notations involving the unit vectors. So I guess I should start out by writing out what the final velocity looks like. Let me organize my space a little bit better. Sorry, I didn't quite think through. So my delta V, actually, let me do it this way. Copy and paste, because I need a space to write more. And let me erase this. Put that in the way. So let me write out what the final velocity and initial velocity are in the whole unit vector notation. So my final velocity, which is this, it has x and y component. The x component should be just I guess they are both kind of simple. So the x component should be, it's going in the negative direction the way I'm defining my coordinates. So it should be minus v naught times, and this is the adjacent side to this angle, so it should be cosine of 45 degrees x hat, plus the y component. This is the opposite side to the angle, so it should be, and it's upward plus direction, so it should be v naught sine of 45 degrees in the y hat direction. Good, that's my final velocity. My initial velocity was simpler. It was just rightward, or in the positive direction. It was plus v naught, no cosine, sine, just v naught x hat. So with those two component expressions for the velocities, I can write out this difference here. That difference is so minus v naught cosine of 45 degrees x hat, let me do the whole thing, plus v naught sine 45 degree. I don't think it matters here, but sometimes you might make a sign error if you don't properly think of the whole thing as one unit, and then minus this v naught x hat. And you collect like terms in terms of the unit vectors. So y hat, it's already the whole thing. X hat, I combine these. So combining those two, you get minus v naught, and then factoring out x hat again. Cosine 45 degrees, and then this minus v naught x hat plus the y component v naught sine 45 degrees. And I'll probably leave it here for now because I'm going to need both of these quantities to get the answer that they're looking for. For the magnitude, I'll need the components, and for the angle, I'll also need the components. So let me actually get numerical value for these here. So I'll have a few versions of Wolfram alpha so that I can switch between them easily. So minus v naught 10 meter per second times cosine of 45 degrees or divided by square root of 2 minus 10 meter per second. So that's going to be the x component. And as it's doing that, let me write down 10 meter per second times the sine of 45 degrees. That's going to be my y component. So with this x component, I want to use this, but let me give it a try. I worry about precision. Some of the questions I think you need to enter with the 4 significant figures, but minus 17.07. So minus 7, and it makes me worry a little bit when I have to when the final number needs 4 significant figures and the intermediate one has only 4, there can be an accumulated rounding error. But let me give it a try, and then if I get a rounding error issue, then I'll do something. 7.071. So, and then I'll be doing 7.071 meter per second. And for the magnitude of the force, I need to get the magnitude of delta v, and actually I'm not done. I have to divide it by delta t to get acceleration, and then I have to multiply by mass. Let me just do the whole thing here. So first, let me get the magnitude of the delta v. I use the Pythagorean theorem, x component squared plus y component squared, and then square root of the whole thing. This is my delta v so far. Let me divide it by the time, 2.00 seconds, and I'm keeping all these units because the units will tell me if I missed something. Like if I stopped here and as I look at the answers, none of them are newtons, that tells me, oh, I forgot to multiply by mass to get force. So let me not forget to multiply by mass and get force. And all of this looks, I think, right. Yeah, 73.9 Newton. Again, that makes me a little bit nervous that that might be graded as incorrect. Never mind. I guess it was close enough. Or maybe this question uses 1% tolerance. I don't know. So that's my magnitude. Let's calculate the angle. So for that, I again need the x and y component. And here, let's see. Can I do? So with the method that I recommend, I think you have to go through multiple steps. So if you are using cosine, then you could kind of let the sine give you the angle, let the sine give you this angle right away, which is what they are looking for. But I recommend using tangent. Recommend using this expression. Tangent theta is the y over x. And when you're doing that, you basically have to be mindful that your answers will only be in this range. So I'm just gonna get the absolute value, the acute angle version of that, and that's gonna be basically this acute angle, and I need to, the angle I'm looking for. So this is the theta that they are looking for, not that other thing. So with the theta, so the tangent theta will give me this acute angle here. Let me call that phi. So tangent phi, absolute value, and then I'll work through from phi to theta. So tangent of phi is so let me do it this way. I'm just gonna copy over the positive version of the number 17.07. 17.07. Right, that's x. So that will go in the denominator. 7.071 will go in the numerator. 7.071. And this time I'm not plugging in any unit, because even though this is technically about the angle of delta v, but the way kinematics works out, average acceleration is in the same direction as delta v, as in, this vector quantity has the same direction as that, and force has the same direction. So I can just work out the direction from delta v, and it'll be the same direction that the force will be. So this is my tangent of phi. So if I do arctangent of that, that'll give me phi. And I want it in degrees, so let me just press enter to get one of the numbers that's in degrees, 22.5. And what I have to recognize from here is that theta plus phi being 180 degrees, theta itself is 180 degrees minus that number I have, 22.5. So I think I can do that in my head. 157.5, 157.5, and yeah. So yeah, that's this question. More of a vector exercise than a dynamics exercise, but you should keep in practice. Vectors are very important.